Okay, so we are going to learn about electrolytic cells, which before we learned about voltaic cells, and this is like the opposite. So we do have to kind of remember what a voltaic cell is. So a voltaic cell is the one that's a battery. It's the one where you say, okay, let's take two metals, let's just say battery, and copper and zinc. And we have two metals, one that gives electrons to the other. So that one is getting oxidized. Oxidation is loss, reduction is gain. Rig. Okay, so we have two metals, one that likes to give electrons to the other. And we say, okay, well, let's not put those metals together. Let's separate them and let's connect them with a wire. And then the electrons are forced to flow through that wire. And now I have a wire with electrons flowing through it. Now I have electricity. And I can put a device, like maybe a cell phone or a light bulb, in the middle of that. And now I have electrons flowing through it. I have an electrical current. Right? So a voltaic cell is kind of using the fact that electrons just naturally, spontaneously flow from something higher on table J, something oxidized to something reduced, and we can capture that in a wire and create an electrical current. Okay, so that happens spontaneously. That's why we're able to walk around with our cell phones every day. So that's a spontaneous reaction. Remember, yesterday our last lesson was about spontaneous reactions. So that's why we can walk around with our cell phones unplugged all the time because it just happens on its own. We do have to like reset them every night, but so voltaic cell is a battery and it's spontaneous. An electrolytic cell is like the opposite of a battery. It doesn't run spontaneously. It doesn't provide electricity. You actually have to like pump electricity in to make it happen. All right. So that's what an electrolytic cell is. It is a cell like the two metals. We call it a cell. It's a thing that needs electricity to make it run. So it is not spontaneous and it is not a battery. Okay. It does not provide energy. We actually have to put a power source in it to make it happen. So, why would we want to do this? There are two uses for this. So, two main uses for this. One is if we want, basically, we want to like zap some chemicals with electricity. So before with the battery, we were taking chemicals and it was giving us electricity. Now we're going to take some electricity, pump it into some chemicals, and do some chemistry. So this isn't as widely used. Batteries are really widely used. We use chemicals to give us electricity. This is taking electricity and using it to make something chemical happen. So like two things would be like if you wanted to like do electrolysis, which would be like electrocuting. If it was hydrolysis, it'd be electrocuting water. So if you wanted to physically separate water, you can't in a lab just go, okay, I'm going to break the H's and the O's apart with tweezers, but you can electrocute them with electrolysis using one of these voltaic cells, and you can separate water into H's and O's. So it's used to do like kind of high level chemistry, so not our everyday stuff. So instead of taking chemicals to give us electrical energy, we're using electrical energy to do some chemical stuff. So I can either use it for that electrolysis, electrocuting something, some chemicals, or I can use it for plating, which like a lot of like cheaper jewelry, we don't want to make it like solid silver. That would be really expensive. So we take a cheaper metal like zinc and we plate it, we coat it in silver, and that can actually be done using this technique. So again, it's taking a reaction that doesn't have happen spontaneously. It's not a battery. We're not getting electrical energy from chemicals. We're actually using electrical energy to make something chemical happen. So let's take a look at how this looks. You'll notice you still have an anode, you still have a cathode, you still have electrons flowing anode to cathode. Anode is still the site of reduction. It's still anox and it's still red cat. That's still the site of reduction. The electrons still flow from anode to cathode, oxidize to reduce. Oxidation is still loss. Reduction is still gain. So in a lot of ways, it's very similar to the voltaic cell, the battery, but there's some major differences that you need to know. And because they're similar but different, you need to know the major differences. So one is that the signs are flipped, and I kind of remember that because you have to like stick a battery in the middle of this, you have to stick a power source in to make it work. Remember, batteries have like their own positive and negative ends. So since they have their own positive and negative ends, they actually give the anode and the cathode different charges. So anode here is actually positive and cathode is negative. So the way I remember this, I say, okay, all my memory tricks are for the battery, for the voltaic cell. Battery is called voltaic cell because it gives you volts of energy. So I'm like, all right, all my memory tricks, anode, cathode, I love cats, so they're positive. All my memory tricks are for that. And then all I'm going to do is for the electrolytic cell, the less common cell, I'm just going to say, okay, the signs are flipped. And I could say, oh, it's because you stick a power source in there and it flips the signs. So I'm going to say everything's still true. It's just that in an electrolytic cell, my signs are flipped. Anode is positive and cathode is negative. So that's all this says right here is that everything's the same for cathode. Everything's the same for anode. It's just that the signs are flipped. So far everything has looked the same. We just have our signs flipped. Everything else is the same. Electrons flow anode to cathode. There are a few other differences. You will see there is no salt bridge. We don't need it to like even out the reaction because this is already like a forced chemical reaction. And a big giveaway that you are looking at a electrolytic cell is that it has some sort of power source in it, whereas the voltaic cell is a battery. Like it provides us energy. An electrolytic cell basically needs a battery. Like it won't happen on its own. We need to make it happen in order to do some sort of chemical reaction. So the big things to know that you're looking at an electrolytic cell is that signs are flipped, no salt bridge, and there's a power source in there. So let's take a look at how you would actually use an electrolytic cell. Like I said, you could use it for plating, like this spoon. I don't want to make it out of pure silver. That would be really expensive, but I would like to give it a nice silver coating. So what you can do is take your two electrodes. One of them is silver because I want to coat it. That's silver Ag. And then one of them is the spoon. Okay. And we're actually going to force this reaction to happen. We're going to force the silver to go over and kind of stick to the spoon. So if I want the spoon to get coated in silver, do I want it to be the site of reduction or the site of oxidation? Do I want it to be the anode or the cathode? So do I want it to be the red fat cat, the one that gains mass, or do I want it to be the anox, the one that loses mass? Well, if I want it to be coated, right, I want it to like be the gainer. So I want it to be the red fat cat. So that's a big thing to realize in this. If I want it to be the thing that's gaining mass and getting the silver stuck to it so it can get coated in silver, I want it to be the red fat cat. I want it to be the site of reduction. I want it to be the cathode. I want it to be the thing that gains mass. So therefore, this thing must be the anode, and ox. And then I'm like, okay, well, reduction, anode, cathode, that's usually positive, but an electrolytic, it's flipped, so that's negative, this is positive. So once you just see that one thing, you go, oh, the spoon wants to get coated, so that must be the red fat cat. That must be the site of reduction, the cathode. So again, usually one little thing can tip you off as to like which side is which, and then you can fill in all the rest. Once I know that that's a cathode, I know it's the site of reduction, I know it's negative. Once I know this is anode, I know it's oxidation, I know it's positive, and I know that electrons flow this way from anode to cathode or oxidized to reduced. So again, what's the whole point of this? It's to do something chemical. It's to use electricity to do something chemical. Whereas the voltaic cell was using chemicals to give us electricity. This is more like doing chemistry, like doing this electroplating, like plating this spoon in silver. I want to draw the silver atoms over. I want negative electrons here. So they're like, ooh, electrons. I want to go, and they're going to stick to the spoon because they want those electrons. They want to get reduced. So I'm drawing the silver over with the temptation of electrons, and that is going to make them stick. And I'm going to chemically plate the spoon in silver. Okay, so that's the point. Let's see if we can answer the questions. The directions the electrons will flow. So once I figured out anode and cathode, I know it goes from anode to cathode. Oh, it's actually already written there too. Which is the negative? Well, red fat cat is the site of reduction. It's the cathode. Normally that's positive, but it is flipped in electrolytic. So the spoon is the negative one. Okay, so which one's positive must be the anode. Usually anodes are negative, but that's the one thing that gets flip-flopped in electrolytic cells, so that must be the silver. Which one does reduction? Well, the spoon needs to be the red fat cat so that it can gain mass and get coated in silver. So it must be the spoon. Which electrode does oxidation occur? Must be anox. Must be I want the silver to lose mass. I want this silver electrode to like have holes in it at the end. It's losing mass. It's sending its silver over here to the spoon to get coated. So there. Which electrode is the cathode? I need the spoon to be the red fat cat so that it can get coated. So if you remember, we said red fat cat because the fat cat, it's the cathode's the one that gains mass. So I want the spoon gaining the silver. All right, so let's just like summarize the two types of cells because it does get confusing. And again, the cell is just like that picture you saw, that setup. Okay, so what's the difference? Voltaic cell is the one that gives you volts of energy. A voltaic cell is a battery. It's the first one we learned. It's what's inside your cell phone. It's electrons flowing from anode to cathode. We capture it in a wire. We use it to charge our electronics. Electrolytic cell is the opposite. So an electrolytic cell is not a battery. It actually needs a battery. It has to have a power source so it can do like chemical things. So voltaic cell is a battery. Electrolytic cell needs a battery. Energy conversion, voltaic cell takes chemicals in your phone battery and turns it into nice electrical energy for you. Electrolytic cell is more for scientists to take electrical energy and do chemical things with it. So you got to memorize that, but if you think about it logically, it kind of makes sense. The flow of electrons, a battery, a voltaic cell works spontaneously. That's why you can walk around with it working all day without being plugged in. So that happens on its own. An electrolytic cell, again, is forced, where we needed to plug it into something to make it happen. The direction of electrons flow is still anode to cathode. Those are the same. We still have red cat. Reduction happens at the cathode. Those are the same. We still have anox. Oxidation happens at the anode. We just have our signs flipped. So I just remember the regular in a voltaic cell I think of as like the regular one. I love cats, and anode is negative, like an antagonist is negative, cats are positive. And then I just remember, okay, an electrolytic cell, that's like the weird other cell, it's just flipped. So that's the only thing that's really flipped. Some giveaways that you might be looking at a voltaic cell is you'll have either two separate containers or at least like one container that's separated into two spots. What is this? Electrolytic cell is one container. This one has a salt bridge. This one has no salt bridge. This one might have a weird object like a spoon or a key that's like being electroplated. Okay, so the big thing is a voltaic cell is a battery. It produces volts of energy as you take chemicals, and use them to make yourself electrical energy. An electrolytic cell is the opposite. You have to plug it into an electrical source to do something chemical. Right, and then finally, let's just sum up our memory tricks for this unit because there are a lot. And if you know them, then if you know one thing, like if you know that one side gets oxidized, then you know it's the anode, you know it has loss of electrons, you know its charge goes up, you know that it's the negative electrode. So if you just know one thing, you can figure out everything else if you have your memory tricks. So let's just go over them. So oil and ox up, those are all I could think of if you wanted to combine them all. Oil and ox up. Oxidation is loss, and oxidation occurs at the anode. You ox up, the charge goes up for oxidation. Oxidation is loss of electrons. Red cat gets fat, rig down. Those are all the reduction tricks. Rig for oil rig, reduction is gain of electrons. Red cat means that reduction happens at the cathode. We like cats, so that's the positive electrode. Fat means that it's the one that gains mass. And reduce down means that the charge goes down. So say you saw the charge went down, then you'd go, okay, reduce down, the charge went down, so that's reduced, so it must be the cathode, so it must be the one that gains mass, so it must be the positive one, so this must be the anode, so it must be oxidation, it must be loss of electrons. So just figuring out one little thing, if you know the memory tricks, you can figure out everything else.